Welcome to my channel. Today's topic is electromagnetic induction. Under this topic, you will learn in depth about electromagnetic induction, including Faraday's law, Lenz's law, electric motors, electric generators, AC and DC, then flux linkage and magnetic flux density, induced current and induced EMF. Moreover, you will also learn about Fleming's left hand rules and Fleming's right hand rules. And where do we use these two rules separately? Also, I have included some examples from Cambridge A-Level's physics curriculum, but my videos are for all the students belonging to any curriculum. Electromagnetic induction is the process by which a conductor or a magnetic field are moved relative to each other to induce or generate a current or electromotive force, that is EMF. This process goes on in the generators at work in power stations, in wind turbines, and on a much smaller scale in bicycle dynamos. The first electromagnetic generator, the Faraday's disc, was invented by Michael Faraday in 1831. Faraday's law of electromagnetic induction is the fundamental operating principle of transformers, inductors, many types of electric motors, generators, and solenoids. Generators convert mechanical energy into electrical energy using the principle of Faraday's law of electromagnetic induction. That is, when a conductor is placed in a varying magnetic field, what happens? EMF is induced, that is equal to the rate of change of flux linkage. Now, flux is the total magnetic field lines passing through a surface. Later in this lesson, you will learn that flux cutting and changes in flux linkage are just two ways of expressing or representing the same thing. The direction of the induced current in a generator's windings or when a conductor attached to a circuit moves in a magnetic field can be determined using Fleming's right hand rule. Now, this is an electric motor and direction of force is determined by Fleming's left hand rule that you have already learned previously when I told you that we find out the direction of force in an electric motor by Fleming's left hand rule. Now, in an electric motor, as I have already told, that electrical energy is converted into mechanical energy, and these motors operate through the interaction between motor's magnetic field and electric current in a wire winding to generate force in the form of torque applied on the motor's shaft. Now, under electromagnetic induction, we will study two cases. First case will be when we will study the generation or production of induced current or EMF when a conductor is moved across the magnetic field. Secondly, we will study the relative motion of the coil and the magnet. Now, here we will study the movement of a straight conductor up and down, and we'll see how the induced current will be generated. Okay, so these red lines are indicating magnetic fields. These are magnetic field lines which start from North Pole and move towards South Pole. So this is a copper rod. It is connected to an ammeter. Please note that there is no battery in the circuit. Now, when you move the copper rod downwards to cut across the horizontal magnetic field, what will happen? An electric current is induced that is indicated by a brief flick of the pointer on the meter to the right hand side or by a small deflection of the meter. When you move the rod upward, the meter again makes a brief flick to the left hand side, indicating that a current has been induced in the opposite direction. There is no induced current if you hold the rod stationary or move it along the field lines, because angle theta will be 0 in this case. Okay, so there will be no flick of the pointer or no small deflection. Now, what is the theoretical explanation behind all this working? Now, when you move the copper rod, as you know already that metal has free electrons, so when the copper rod is moved downwards, its free electrons move with it. When a charge moves in a magnetic field, you have studied already that it experiences a force. Now, direction of force on each charge is determined by Fleming's left hand. Now, direction of force on each electron is determined by Fleming's left hand rule. When the rod or electrons move downward, what happens? Force is to the right. This is according to Fleming's left hand rule. As magnetic field lines are in this direction, electrons are moving downwards, then force will be on the right hand side, towards the right hand side, because all these three quantities are mutually perpendicular to each other. This we have learned in previous videos. Okay. Now you also know that an electron moving downward is equivalent to a positive charge moving upward. Now one end of the rod is made short of electrons. Because electrons are moving downward, what will happen? The upper end will become short of electrons and it will be positively charged. And where electrons will accumulate in the downward direction, that end will become negatively charged. Thus, there is now a voltage across the ends of the moving rod. It will be more clear in the next slide. Now just look at the magnified view of the rod and the magnetic field. When the rod is moved downward, what happens? Electrons travel along this rod. These are free electrons, right? And this end will become negatively charged due to accumulation of negative charge or electrons. And the other end will become positive charge due to loss of electrons. Or it is left short of electrons, hence it is positive. Thus there is now a voltage across the ends of the moving rod. Correct? Like in this way. If you join the ends of the moving rod to form a complete circuit, what will happen? The induced voltage causes a current to flow through the circuit, which will be indicated by the flick of the ammeter. The induced voltage is a source of electrical energy, that is an EMF. So it will behave like a cell, right? One end is negative and other end is positively charged. Now the key point here is to note that an EMF is induced when a conductor is moving in a magnetic field like this, even if there is not a complete circuit for a current to flow. Now this is the second case, induced EMF due to the relative motion of the magnet or the coil. Here we move magnet inside or out of the coil, and here coil is moved in the magnetic field. The detail will be presented in the next slide. Now we will study two cases. When the magnet is moved across a coil, firstly when it is moved inside the coil or the magnet will enter inside the coil, what will happen? When you move the magnet into the coil, an EMF is induced across the ends of the coil. This EMF drives a current around the circuit and the meter gives a flick. In second case, if you move the magnet out of the coil, like indicated by the arrow, then the induced EMF is in the reverse direction and the ammeter gives a small deflection in the opposite direction. If you move the coil instead of the magnet, suppose we move the coil instead of this magnet, what will happen? The meter still shows a current. It means that an EMF is induced whenever there is relative motion between the magnet or the coil. Now here I have shown a portion of the magnetic field lines of a bar magnet to study what happens when the coil cuts through the lines of flux. Now Michael Faraday's law of electromagnetic induction states that an EMF is induced when a conductor cuts through lines of flux or there is a change in the flux linkage of a coil. Now what happens? As an example, when the coil is moved from position A to position B, we say the number of lines of flux linking it changes from 5 to 9. Lines of flux 1, 2, 3, 4, 5, and here these are 1, 2, 3, 4, 5, 6, 7, 8, 9. So we say a change of 4, or we say that the coil has cut through 4 lines of flux. So this is the same, like two ways of describing the same thing as I have mentioned initially. Now this is another example when we move the magnet inside the coil. Turns off a solenoid, for example. So what happens? there is a change in flux linkage. Like initially there are 6 lines, and at the end, at this position, there is only 1 line. So flux cutting or changes in flux linkage is 6 minus 1, 5. So these are again two ways of looking at the same thing. Now we will study factors which affect induced current in case of a straight conductor, and then in case of when we study the relative motion of the coil and the magnet. Now first of all, factors affecting induced current or EMF for a straight conductor. Number 1, the magnitude of the magnetic flux density, the length of the wire in the field, and the speed of the movement of the wire. Now secondly, for a coil of wire, the induced current or EMF depends on the magnitude of the magnetic flux density, the cross-sectional area of the coil, the number of turns of wire, the rate at which the coil turns in the field. It simply means that the size of the induced EMF across a coil can be increased by using a stronger magnet, a coil with more number of turns of wire, with a greater cross-sectional area, and by moving the magnet faster. This is because the larger and the faster the change in flux linkage of the coil, the greater will be the induced EMF. Now here, this is just a demonstration of Fleming's right hand rule, which is used in generators. See the magnetic field lines from right to left, from north pole to south pole, and the movement of the rod or the conductor is upward. So the direction of the induced EMF using Fleming's left hand rule will be in the towards X. Okay. So it must be noted here that both rules, Fleming's right hand rule and left hand rule also, are basically used for the direction of the force, but for generators we use Fleming's right hand rule, and for electric motors we use Fleming's left hand rule. Thank you for watching. Lenz's law. Statement of Lenz's law is that an induced current or induced EMF will be established in a direction so as to produce effects which oppose the change in flux that is producing it. So as I have already told that according to Faraday's law of electromagnetic induction, induced EMF is proportional to delta n phi over delta t, where delta is the small change, n is the number of turns, phi is the flux, and delta t is the time interval. We know that in order to change proportionality sign into equality sign, we multiply right hand side by a constant quantity, and in this case, working in SI units, constant of proportionality turns out to be 1. So we can write induced EMF is equal to minus n delta phi over delta t. We take out n, as n is the number of turns which is constant for a coil, and minus sign represents that the direction of induced current is opposite to the cause that is producing it. So induced EMF will be equal to number of turns times delta phi over delta t, or rate of change of flux linkage. So I have introduced a slide as I have already told, and kindly go through the next slide to clarify your concept regarding flux linkage. Now here I have shown a portion of the magnetic field lines of a bar magnet to study the what happens when the coil cuts through the lines of flux. Now, Michael Faraday's law of electromagnetic induction states that an EMF is induced when a conductor cuts through lines of flux, or there is a change in the flux linkage of a coil. Lenz's law. There are two explanations of Lenz's law. To determine the direction of the induced EMF, we need to find out which end of a wire or coil moving in a magnetic field becomes positive and which end becomes negative. Fleming's right hand rule was discussed in the last lesson. This rule gives the direction of an induced current and is a particular case of Lenz's law. We will also see how Lenz's law summarizes principle of conservation of energy. Now, this is an illustration of Lenz's law. In the first case, as the north pole of the magnet is moved into the coil, an EMF is induced which drives a current through the circuit. Using the right hand grip rule, you can see that the current produces a magnetic field with a north pole at the end of the coil nearest to the magnet. I have introduced a slide from the previous video on right hand grip rule just for your clarification once more. Now, according to basic law of magnetism, we know that like poles repel each other. Then what will happen? There will be a force of repulsion between two north poles. So the coil repels the incoming magnet, and thus an induced current opposes the change in flux. In the second case, as you move the north pole out, according to Lenz's law, the coil needs to attract the receding north pole, because according to right hand grip rule again, this side of the coil will become south pole, and according to basic law of magnetism, unlike poles attract each other. Hence the direction of the current is reversed. Now Lenz's law is a result of the conservation of energy. If you move the magnet into the coil, you feel the repulsive force. You have to do work to move the magnet against this force. And so energy is transferred from you or the system that is moving the magnet to the electrical energy of the current. In Faraday's law, usually you see a negative sign that always reminds us that the EMF is always induced in a direction so as to oppose the change in flux. So kindly revise right hand grip rule as I have stated in the next slide. And when we change the direction of the current, the change in direction of the current will be indicated by the change in direction in the needle of the galvanometer, as can be seen in these diagrams. Now we use right hand grip rule to find out the direction of the magnetic lines of flux of a solenoid. A right hand grip rule states that curl the fingers of the right hand in the direction of the current, and your thumb now points out in the direction of the lines of flux inside the coil towards the end of the solenoid that behaves like the north pole of the bar magnet. A bar magnet is dropped vertically downwards through a long solenoid which is connected to an oscilloscope. The oscilloscope trace shows how the EMF induced in the coil varies as the magnet accelerates downwards. Now there are few questions and I will explain to you how to answer these questions. Part A is explain why an EMF is induced in the coil as the magnet enters it, shown by section AB of the trace. As there is a sudden increase in the flux linkage for the coil, so there will be an induced EMF. B part, explain why no EMF is induced while the magnet is entirely inside the coil, shown by part BC of the trace. The answer to the question is, as there is no change in the flux linking the coil, hence there will be no induced EMF because the motion is parallel to the field. C part is, explain why section CD shows a negative trace, why the peak EMF is greater over this section, and why CD represents a shorter time interval than AB. The answer to the question is, as magnet leaves the coil, there is a decrease in the flux linking the coil, hence the EMF produced is in the opposite or negative direction. The induced current is in the opposite direction according to Lenz's law, and peak EMF is greater because magnet is moving faster because of acceleration due to gravity. So the rate of change of flux linkage is greater in this case. Electric generator. An electric generator converts mechanical or kinetic energy into electrical energy. Two fixed strong magnets, which are permanent magnets, they are placed with their opposite poles facing each other. The magnetic field is concentrated to the coil by the structure of the soft iron, that is, they are curved inwards. Both AC or DC generators work on the principle of electromagnetic induction and are essentially electrical motors working in reverse. Now, an alternating EMF can be induced by rotating either a coil in the magnetic field or by rotating a magnetic field within a stationary coil. That is, in some cases the conductor moves, in other the field lines move. Alternatively, we may say that the flux linking and area changes. Now, generators supply power or electricity to anything that requires AC supply, like lights and fans in houses, or large motors and air conditioners or air conditioning systems in an industry. Now, power stations supply electricity to thousands of houses by spinning a giant turbine. A coil of wire is attached to the turbine and placed in a magnetic field to generate electricity. As turbine spins, coil spins, and it produces an electric current, which is used to light up things. Now, this electrical current is produced through electromagnetic induction, which is a technology that was discovered by Michael Faraday more than 200 years ago. Now, these devices are called electric generators. Today, we will consider and discuss the case when a rectangular coil rotates in a magnetic field. Now, consider a coil that rotates in a magnetic field. Each end of the coil is connected to a slip ring. The slip rings rotate with the coil and press against stationary carbon brushes. Each side of the coil always makes contact with the same brush. Now, what will happen if you rotate the coil at a steady speed? As it turns, the flux linkage of the coil constantly changes and the pointer on the ammeter swings from side to side, showing that alternating current or AC is induced. Therefore, in an AC generator, the electrical current reverses its direction periodically. We will also study a graph that will show how the size of the induced EMF changes as the coil rotates, makes one rotation in the magnetic field, and one complete rotation of the coil gives one cycle of AC. Now, electric generators are of two types, AC generator and DC generator. Now, let's see what is the difference between these two generators. In an AC generator, we use slip rings, and in a DC generator, we use split rings or a commutator. Now, let's see what is the difference between these two. A slip ring is a continuous ring, whereas a commutator is segmented. Slip rings provide a continuous transfer of power, signals, or data. Brushes and slip rings arrangement is shown for an AC generator here. Each ring is connected to one wire only. See here. Each ring is connected to one wire. This one is connected to this wire, and this wire is connected to this ring. Now, commutator is a device or attachment for reversing the direction of flow of electric current through which electrical connection is made, and which ensures the current flows as direct current. Also known as split ring, as it has a gap. See this gap. A commutator reverses the direction of the current every 180 degree, and so the output is DC. Now, slip rings are used in any application that includes a rotating platform, from industrial to wind turbines, in medical imaging machines like CT, MRI, and even in amusement park rides. They can also transmit analog and digital signals from temperature sensors and have many other uses as well. Now, this is a layout of an AC generator. See these slip rings, these are carbon brushes, and this is the front view of slip ring. And this is layout of a DC generator where we use split ring commutator. See the gaps, okay? And this is the load. This is coil. These are two permanent magnets. These are carbon brushes which are colored in gray, and this is the wire. Same, this wire coming through this brush, and this wire is coming through this brush. Now, this is the graph for an AC generator, the output from an AC generator. See, this is time axis and this is EMF. This is peak EMF denoted by E0, and one time period is equal to one complete cycle in which a coil rotates. Okay, one complete rotation of the coil gives rise to these values of EMF. See, the EMF is alternating, and this time period is equal to 2 pi over W, where W is the angular frequency. And this is the DC output from a DC generator. These are split ring. This is split ring commutator. These are brushes. This is angular frequency, and this is the load. Now see the different orientations of the coil during one complete rotation. These are 3 orientations. Now you may see that the rate of change of flux linkage is maximum when the coil is moving through the horizontal position. One side is cutting rapidly downwards from here, whereas the other is cutting rapidly upwards. In this position, we get a large induced EMF. As the coil moves through the vertical position, what will happen? The rate of change of flux is 0. The sides of the coil are moving parallel to the field lines. So when the sides of the coil are moving parallel to the field lines, not cutting them, then what will happen? There is hardly any change in the flux linkage. Okay. Now this is the graphical representation of the flux linkage and the corresponding values of induced EMF. Okay. So changes in the magnetic flux linking a coil gives rise to an alternating EMF. Now what is this? These are the orientations of the coil, okay, in one complete rotation. These are vertical positions and these are horizontal. Now according to Faraday's law, what happens? The induced EMF which is produced is equal to minus rate of change of flux linking the coil. Now in first case, see here, in this position, when the flux linking the coil is maximum, the rate of change of flux is 0 when the wire or coil is in the vertical position. Hence the induced EMF will be 0. Now in second case, when the coil is in the horizontal position, when the flux linking the coil is 0, what will happen? The rate of change of flux will be maximum, and hence the induced EMF is also maximum. So in one complete cycle, you can see varying EMF. Okay. And so we can see that for a coil like this, we get a varying EMF. This is how alternating current is generated. In practice, sometimes it's simpler to keep the large coil fixed and spin an electromagnet inside. Now in the next slide, we will discuss an example, and we will also see how can we increase the size of the peak EMF. We have studied that induced EMF is equal to minus rate of change of flux. Now the basic equation from where we derived this equation is induced EMF is equal to BANW sine theta, where theta is the angle between plane of the coil and field lines. B is the flux density in Tesla, A is the area, N is the number of turns, W is the angular frequency. Now we know that maximum value of sine is 1, and it will be 1 when theta will be 90 degree. That is, B and A are at right angle to each other. In that case, this equation will reduce to this equation, and it will give the maximum value of induced EMF, which is denoted by E0. So at this point, the wires of the coil are cutting through the flux at right angles. Now what we can do to increase the size of this induced EMF, this peak value of EMF? It is obvious that this peak EMF depends upon 4 factors. So in order to increase the size of the peak EMF, we need to increase each of this factor, okay? Like we use a coil with more number of turns, we use a coil with a large cross-sectional area, we will increase the strength of the magnetic field, and we will increase the frequency of rotation of the coil. Okay, thank you for watching.